We also need something called kinematics, right? We need the kinematic relation again with coordinate notation. This is the kinematic relation for the strain. Epsilon KL is 1/2 derivative of another vector u with respect to x plus the symmetrizing term. I should mention that, I should make it clear that that is L, not I. Okay? Right, so we have this kinematic relation. In direct notation, this would be epsilon equals the symmetric part of the gradient of u. Okay? All right, so we have these components of our problem. Okay, so let me just go back here for a second. So we're given data in terms of these vectors u, g, t bar, and f. We're given a constitutive relation relating the stress to the strain through the elasticity tensor. Okay, and we're given this kinematic relation. Okay, so given all this, what we are faced with is finding u, okay, which is, I'm sorry, I need to stick with coordinate notation here. Find ui, okay, and again ui is a vector, right? It's a component of a vector, so this really is saying that u belongs to R3. Okay, again parenthetically we have the direct notation there. Okay, find ui, right? Which so ui is our solution field, and you probably know, if you know some elasticity, you know that this is the displacement field. Okay, so find ui such that the following hold. Okay, let's first write out the PDE itself. The PDE is the following: sigma ij, sigma ij comma j plus fi equals 0 in omega. Okay, and if you already know it, that simply means that the stress divergence, the divergence of the stress plus f equals 0. Okay, this is sometimes called the stress equilibrium equation. Okay, so sometimes called the quasi-static stress equilibrium relation. All right, okay, so that's the PDE. Boundary conditions. U I equals U given sub I on the Dirichlet boundary. But here comes the rub. We have a vector problem, right? So if you look at the equation that we put down, the PDE, this PDE, what we need to recall is that in all of this, we need to recall that I comma j equals 1, 2, and 3, right? So when we look at the PDE, we actually have 3 PDEs there, right, for each value of I. Not a big surprise, because we are talking of finding a field which is itself a vector, right, which has 3 components. So we're really solving 3 PDEs. Okay, it's a vector PDE. What this means is that we need boundary conditions for each component of our field, of our solution field, right? But then each component of our solution field could have a Dirichlet boundary condition defined on a different Dirichlet boundary. Okay, so on this Dirichlet boundary itself, we can have a subscript. What this means, when I go back, well, let me draw it right here. What this means is that we have our basis, we have our domain. It means that for each component, right, I could have a certain Dirichlet boundary. Okay, right? Let me actually give this a specific component. Let me suppose that this is the Dirichlet boundary for the component 1. All right. However, when I come to component 2 and 3, I am free to take on to give them different Dirichlet boundaries, right? So and these could overlap or not. Right? They can be completely arbitrary, right? No implied relation with each other. This simply comes about from the fact that we're solving a vector problem, right? And of course, it's elliptic, so we do need boundary conditions everywhere. Okay? So that's for the Dirichlet boundary. Well, the same sort of thing happens for the Neumann boundary, because each of those Dirichlet boundaries has as its complement a Neumann boundary, and I think I'm going to denote this as omega, well, obvious, right? Omega, partial of omega t bar sub 1. We have partial of omega t bar sub 2, and partial of omega t bar sub 3. Okay? Of course, in each case, each set of Dirichlet and Neumann boundary conditions are complements of each other. Okay? So here we have, okay, so where does the Neumann boundary condition come in? It comes in to say that sigma ij nj equals t bar I on partial omega t bar sub I. Okay? What we have is that the boundary, okay, is always equal to partial omega u sub I union partial omega t bar sub I, and that each Dirichlet boundary for a given component of the solution is disjoint from its Neumann boundary. Okay? This holds for I equals 1, 2, 3. Okay? Here's what this means. 3 dimensions. this is our continuum football now, right? When it comes to boundary conditions, what we're saying is that for each component of space, right? For each direction as defined by our basis vectors, we have a Dirichlet condition for the corresponding component. So U1, so maybe U1 is specified on the maze part of this football, and the corresponding traction component, right, which would be obtained through this relation, right, the corresponding value of T bar 1, right, when we're talking of this. Okay, so if U1 is specified on the maze part, T1 is specified on the blue part, right? And then again, if U2 may be specified on the part of the football that you can see, right? And T2 is specified on the opposite part, okay? U3 may be specified on some, I don't know, some combination of the maze and blue. Maybe that maze part, this blue part. On its complement is where T3 is specified, okay? What this corresponds to, if you've studied problems of elasticity or mechanics, is the fact that on a given boundary, we may often not be controlling all components of the displacement, okay? So it's common in problems of elasticity to do so-called uniaxial tension problems, right? So supposing this were my, this were a bar, and at this end I decide to hold things fixed. So there are different ways to do this. I may choose to specify that on this surface, on this edge of this set of Lego pieces, I control all displacement components, right? U1, U2, U3. I may choose to say all of them are 0, right? And then I may choose to load this thing up, right? Alternately, there is another version of tension. That is what I've just described is not truly uniaxial tension. It turns out that it develops stresses at this end in directions other than the longitudinal direction. Instead, I may choose that on this boundary, I specify only this component, let's call it the E1 component, the U1 component, to be 0, okay? And the other two components are allowed to move around to relax, so that now when I pull this bar, because of something called the Poisson ratio in linearized elasticity, this bar will tend to shrink in size. It will tend to contract in the other two dimensions if I pull it one way. Then I'm allowing points on this surface to also move in the vertical direction and the direction towards you, okay? So elasticity gives us the freedom to do that on a single boundary, right? So there are many ways in which we can combine the Dirichlet boundary conditions on any given surface, and indeed for the traction conditions too. All right. So in the problems I just described here as uniaxial tension, often the lateral boundaries are free of traction, okay, which means the traction on those surfaces is 0. Sorry, it's 0. Now, when I pull on this end of the bar, I may choose to do that by also specifying the Dirichlet condition, right? I may specify that I'm going to pull this end. There we go. I'm going to pull this end to some distance, right? That's a Dirichlet condition. Or I may choose to say that on this surface, I'm specifying only that the traction along this direction, this longitudinal direction, is controlled. Only that component of the vector. Okay? I'm free actually to specify the displacement components in the other two directions, right? So there are all kinds of ways in which we can combine them, right? And these are actually highly relevant for physical situations and lead to, they're completely different boundary value problems. They lead to solutions that are different in important ways. Okay? But the important condition to always be satisfied is that the union of the Dirichlet and Neumann boundaries for each component always essentially give a union that gives us the entire boundary, and that each Dirichlet boundary and Neumann boundary for a given component direction are disjoint. Okay, so this is just a beginning step, an early step towards the strong form of elasticity. I'm going to end the segment here, but when we return, we are going to say a little more about this because it's important to understand what elasticity is trying to do here. I will also write up the direct notation for this problem and say much more actually about many of the ingredients of this problem. Again, it's important to understand that as we are setting up numerical methods for it. The complexity comes entirely from the fact that it's a vector problem. All right, we stop here.